So, you pretty much a bit right. It has no connected finite. No important. But you could have non-separable algorithm if you have some connected finite speed.
That's what we hear.
We should somehow like the alpha T or mu T. You take review, then it's fine.
It's zero, and it's just not the definition of the figure. It's because you take the canonical bundle, and of course, as long as you are on the curve, it's also different because you can trust that it's beautiful can be. You take you take the canonical bundle, and then there are two components, and because this is not the figure. It's already covered. It can be and covered. If you take the inverse series of the n. The trust. That's your figure.
f from x to y can be transversalized, so it can be flattified by log alterations. I'm going to use this following way. Can you see if I put this here? Because I want to keep it.
Probably better if you
Not on this.
Okay. I want them. Sorry, there you had a question.
Do you have like proper load smoothness hypotheses so that it'll be a flux or do not?
Yeah, I don't care for this talk. It is true in the case that we're looking at, but I mean the things are proper that we're looking at. So yeah, I mean what you're saying is true. It's not relevant for this talk, so I don't want to go there basically. Oh, I'm ready. Oh no, there's a third one.
Sam,
Yes.
can you maybe read out the second condition in your definition of profit when it comes yours? It's difficult to read.
Sorry. It says that the integral structure of the cone complex needs to map onto the integral structure of the cone complex.
Ah, okay.
I'll draw you some pictures. But, so what does this mean? Right? So cones maps onto cones. So cones maps onto cones means that something like this does not happen, because here you have a cone that doesn't map onto its image. So this is okay. So this is okay, and this is not okay. And the second condition says that also you need that the integral points map onto the integral points. So that will be okay. Something like this would not be okay. It's still okay on this cone, but maybe I take only the third point here. Okay. Okay, so how am I using all this? I'm using it in one way only, and that's we're starting with this family C D over S. And now I have a modification here. So R is a log alteration, let's say. Doesn't matter. Then canonically, I'm going to get a diagram CR to DR to SR. So let's say this was F. Okay, so here, this is going to be a log curve. This is going to be a log curve. And this is going to be flat now. Right. So what I'm saying is, you start with a diagram. This map may not be flat. This map is definitely not flat because it's some kind of blow-up. But I have a canonical diagram which flatifies this and keeps my curves to be log curves, but only on sufficiently high blow-up of my bits. Okay. But I'm gonna use this construction. So is this okay?
How do you know that the process terminates? I mean, you subdivide D, and then you have to go back down and subdivide S, but then you might have to go back up and subdivide C, right?
Yeah,
and then how do you know that you don't have to go on forever?
Can I show you after?
Okay.
Yeah, it's easy, but I mean I'm gonna mess it up.
Yeah.
Yeah. Yeah, so anyway, so if you hated this discussion, it's fine. The consequence is that I take as input this data, and as output, semi-stable reduction spits out this data. Okay, and it's important to me that I blow up this curve to some C prime here. So doing this is some kind of violence on the original diagram. This map won't be flat, and this won't be flat, so this won't be a curve. But you can fix it. You make this a curve, make this a curve, and the map is flat. Okay, so that's, remember my method was semi-stable reduction plus log peak plus compactify Jacobians, and this is the background I need from semi-stable. This is the input that comes from semi-stable reduction. Okay. Okay. So the second is logarithmic Jacobians. And maybe let me start with some kind of schematic, but it's not 100% true to life, but I find it quite helpful. So I want to explain that the y, the Jacobian of a nodal curve is pathological. And there's two pathologies. So imagine you have some family of nodal curves, and now it degenerates into a nodal curve. So pathological in this context is going to mean that the curve group, say this is C and this is S, is not going to be proper. And it's neither universally closed nor separated actually. There's two pathologies. The first pathology is you can imagine you have a line bundle on the, let's say, general fiber, which I'm going to draw as a divisor, and it wants to collapse into the node. So that means that the limit is not going to be a line bundle. And of course, the divisor picture is not 100% accurate because it might be possible that you can find a linearly equivalent divisor that doesn't want to go into the node, but sometimes you can't do that. And the second pathology, sorry, was there a second pathology is you can have this kind of vertical divisors. And this kind of vertical divisor is always a limit of the trivial bundle that's non-trivial. So that's an abstraction to separate us. So line bundles collapse into nodes. That's one pathology which causes not universally closed. And the other pathology is vertical and bundles. This causes lack of separateness. Anyway, these have a name, they're well studied, they're called twists. So I mean, fixing this problem has been studied for a long time. Has a lot of solutions. I want to start with one, which is to cheat, essentially. And it says that we have, let's say we have our curve C to S, and it's a log curve, so there's a log structure. So there's a log structure. And this kind of argument is telling you that essentially the OC star torsors are pathological. So the idea, actually this idea, is to use MC group torsors to compactify the space. So, okay, so let me define. So the log Jacobian CS is a group of MC group torsors. Isomorphism classes of MC group torsors. C. And it is a fact. And so it's a fact. The log, maybe that means that's possible, but big. Yeah. So the log Picard functor is one proper log two log smooth. Three group. So in a way, it's a solution to this problem, right? So it reduces, so let's say 4. It reduces the pick over Q. Remember, my S was always this normal crossing square. But the problem is that it's not representable. And by not representable, I mean it's not representable by an algebraic stack of a group structure. It is, on the other hand, what you can reasonably call. So it is what you can say. It is an algebraic space in the category of log schemes. So you could reasonably call it an algebraic log stack, and that has some technical meaning. And it means that it satisfies the descent of log et al maps. And it means that it has some kind of finite diagonal. And it has a cover, a log et al cover. By scheme, but if you haven't spent time with this list of adjectives shouldn't really mean anything. So let me just give you a little bit of practical.
There's the point that there's no sensible notion of minimality.
That's exactly the point.
And it's nothing. It's not even. There's not even like some maybe infinitely generated monad that would be minimal.
No,
it's just
so the minimal thing wants to be a gate. It can be. So let me erase.
Is it really satisfying for all log
My base is log smooth in this talk, okay. So yes. This is, in fact, in the beginning I had some assumptions. This is exactly where they come in. So let me give you some practical way to think about this. Let's say user spread. So one is it also has a tropicalization. Remember, before I had my x, and it had some sigma x, some kind of Hom complex that captures the geometry of the divisor. Well, this thing is not a representable thing, so I can't write it like this. But it still has a tropicalization. It's an exact sequence. This is the multi-degree zero bundles. Here I have the logarithmic Picard, and then it has a fan, which is called the tropical Picard. And how does this look like? Well, here was my family of curves. Here was one complex of the base. Over it was some family of tropical curves. And so it was some tropical curve and the lengths were varying as I was moving around. And the Jacobian is going to look like a family of tori. Also a moving family of tori. That's one part of the structure. Second part of the structure.
So this is also not representable for the same reason. Right?
Yeah, the reason that the log peak is not representable is essentially the reason that tropical peak is not representable, because it is a torsor under something representable. Okay, two, the polyhedral decompositions. Decompositions of tropical peak correspond to the toroidal compactifications of the multi-degree zero Jacobian. Okay. So I have this family of tori, and yeah, so in this archetype I had X and I had sigma X, and every time I give you a map, I could make a new space over it.
I think it's not multi-degree zeros and in the toroidal compactification, it's just degree zero.
Why not? Okay, fine. Let's say of the interior. How about that?
Okay, then.
So here, right? So here, I have the complex, and I could subdivide it, and then it took my scheme, and it gave me some kind of blow, right? And it works the same way here. So you can take this family of tori and break it into pieces, give it a polyhedral decomposition. And what you get out of it is a toroidal compactification. So if delta was a subdivision of tropical peak, then you get a space, peak delta, living over log peak. And although this space is not representable, this becomes representable. So you can think of failure of representability as failure of this guy to have a polyhedral structure. So it's the so you can think of it as the minimal toroidal compactification. The third practicality is invariance under log alterations. So that says that if you take my C to S and you subdivide, you take one of those log alterations, you get a new family of curves. And nevertheless, log peak is not going to change. The fourth thing is that it has a cover by peak. So what do I mean by this? So I can take peak with any one of those families, and I can map them to log peak P prime over S prime. here under this connecting homomorphism, right? When I have a log curve, if you give me a line bundle, so an OC star torsor, I can push it forward and get an MC group torsor. So if you give me a line bundle on this blown up family, I can make an MC group, MC prime group torsor, but this is the same as the original thing. So I have a map from the Picard of every semi-stable family to log Picard, and their limit are this. So this forms a cover. That's okay, and the fifth point is what is the kernel of this map? So what is the kernel of this map? Pick from C prime to S prime to log pick. Well, you have to look. You have to look at this exact sequence here. And what you'll see is that the kernel is 8,0 of MC group. Right, so the elements of H1 or C star come up to 0 in the MC group torsors are exactly the elements of MC bar group. And let me tell you as a fact, this is exactly the group of piecewise linear functions of the tropicalization. This is what Johannes was talking about yesterday. So the kernel are the line bundles of the form O alpha or alpha ideal function. Right. Prime. Okay. By the way, the piecewise linear functions in this picture here, the piecewise linear functions in C. So there's multiple ways. I need to erase. Are there any questions?
So the logic is a piece of groups for the ETH or FDPF topology, or what?
It is a set of groups for both the ETH and the FDPF topology, and in fact even more. It is a set of groups for this, the whole log FDPF topology. At least when you assume that the base is nice, the base of the operation.
There's something slightly confusing about this thing, because on the one hand, you're thinking residential, so you're thinking of everything on the big side, but then when you say it's a sheet in the local topology, you're thinking on the small side of the text. So both things are true, but they're statements that stated on contract.
I couldn't see.
Because it's not representative.
You can cover with
So
some.
it has it covered by it. But then when you say that, they're talking about objects on the big side, and then it's another sheet for the local topology. So
But yeah, I mean, maybe as a first approximation, it's a good idea to think about it in terms of its fun. Right, so its fun is just a varying family of tropical linear varieties. And the non-representability means that the torus does not have a polyhedral structure. It's one cell. But to give it representable I was to pull the line bundle further, it's the same element, but also all the line bundles that come from piecewise inner functions are trivial. That's a presentation, whatever you prefer. But okay, so now I can give it instruction, and it's kind of it's not that difficult. So I'm going to start with my original family. And so I had C to be the curves over S, the Malthus log flat. And I'm going to take a torsor. I'm going to take an element on the log peak of C. Okay, lambda. So that means that I can find a blow up C prime, and I can find a line bundle on C prime that represents it. So let's say induces lambda. So now I'm going to run semi-stable reduction. I'm going to run semi-stable reduction. And I'm going to get my diagram in the beginning. Okay. So now this map here is flat. So I can push, I can take the norm of that line bundle, L, let's say, goes back to CR, and that is going to give me an element of peak BR over SR. Then I can push forward one peak BR SR. But because SR differs from S by a log alteration and BR differs from B by a log alteration, by invariance, this is the original. It's the log peak of the original. Okay. So that gives you a norm map. So there's a norm map. So this implies that there's a norm map. Log peak. C log peak. So I'm going to use my I don't know, my own definition, I guess. But my definition is going to be that the log Prym of F is going to be the kernel of the normal. And the log from log peak of C over S to log peak. I'll take some components of identity. And now this is a space that's like log peak. It's also non-representable, but it satisfies the same properties. So in particular, it has a fund, which I don't have time for, but it has a fund And its polyhedral subdivisions correspond to schematic models of this closed Prym. So let me explain now how you can get, okay, so this is compactification, but it's not algebraic. So with the last few minutes, let me just explain how you can get schematic models. Well, one way is kind of existential. It just says find any polyhedral decomposition. Of course, if you've thought about this problem, you know that it's not easy. But there is a good method for making schematic models. And this is schematic models of PIC already. And I think Philip was going to talk about this afterwards. But so a good way to make schematic models is to choose what's called the numerical stability condition. And it's also not super important exactly what this is, but okay, let's going back to this pathology. So a numerical stability condition is just going to be a collection of numbers for every component of every fiber, and they need to smooth out correctly. And so when you smooth the fibers, the degrees have to add, and when there's a monodromy, has to respect this monodromy. And then this is, by the way, this is sorry, this is a work of like almost 50 years. It goes from Alda Sabri to Caporaso, and so on. I think I'm using the version due to Cas and Pagani here. But how this problem is solved is, so in some way, we can say that this problem was solved here by imposing an equivalence relation, by killing the twists. Of course, it's not completely fair to say that, but anyway, let's say this for now. So this way chooses a representative. And how it does this, it says, if you want to fall in the divisor, you're allowed to blow up and receive it, but only once. You can blow up its node, but at most once. That's called the quasi-stable model. Quasi-stable model. And then you don't allow all the line bundles. You choose out of all the possible limits, the one whose multi-degree is closest to phi. So there exists a unique representative closest to phi. At least if you choose your stability conditions sufficiently generically. It has to be sufficiently. And now, I mean, yeah, and so this gives a space pick phi. And those are special. Those are the toroidal compactifications that interact well with this cover property. So the big phi are exactly the toroidal compactifications that play both roles. They both come from a toroidal compactification and they fit in this cover. Because they live, so they map to log peak, but they also live in this universal Picard type that we heard about yesterday, if you wish. They have like a dual role. So I'm going to define, and that will be the last thing. So here is the proposal for Prym phi, and this is going to be an algebraic space, and its object key points are going to be the following. They're going to be quasi-stable models of CFT, a phi stable line bundle on C prime, such that the norm of the line bundle, so I'm going to write it down here, such that the norm of L pulled back to, this has to CR is O of beta. And beta is a piecewise linear function on VR. Okay. So I know this was fast, but okay, so maybe let me just summarize what the arguments are. You use this compact space and its compatibility with semi-stable reduction to get norms. That defines a compactification in the log world, which is not representable. But then, to find a representable one, you have to find a model of its fund. And the way you can do this is you can choose a stability condition from the Picard group. And the end result looks like this. Okay, I'm gonna finish. I think